Okay, so we are finally getting into logarithms. So 10.4, we are talking about logs. All right, so part one is using logarithmic notation. So since the exponential function f of x equals 2 to the x is a one-to-one function, we know that it has an inverse. And if you don't believe me, go test it out with the horizontal line test. Let's try and write an equation for the inverse function, right? So first of all, we're going to replace f of x with y. So I'm going to write y is equal to 2 to the x. Okay, then we want to interchange x and y. So I'm going to write x is equal to 2 to the y. But now, if I wanted to solve for y, I am a little bit stuck, right? 2 to the y has y in my exponent. I don't really know what to do here. We are unable to write an equation because we don't know how to solve for y yet. Logarithmic notation, which we are about to learn, will allow us to finish solving this, okay? So let's just get right into it. So the symbol, or like the wording, log base b of x equals y, means that b to the y is equal to x. And the way that you can kind of remember this is like this little like circle method thing is like b to the y is equal to x, right? So b to the y is equal to x, okay? And we say log base b of x equals y as the log of x to the base of b, or log base b of x. So this b will typically be a number. So you'll have like log base 2 of x, or log base 2 of 8, or something like that. And the way we say it is log base, whatever your base is, and then of whatever you have the log of. So like 8 or x or whatever. Okay. So again, log base b of x equals y means that b to the y is equal to 4 to x. And so we have this formal definition for a logarithmic definition. So if b is greater than 0 and b does not equal 1, then y equals log base b of x means that x is equal to b to the y for every x that is greater than 0 and every real number y. Okay, so what we're going to do now is we're going to practice. So first off, we want to write each as an exponential equation. So we want to write each of these logs as an exponential equation. So first off, we have log base 2 of 25. And that means that, again, we can do our little circly guy. I actually wrote that problem down wrong now that I'm looking at it. This is supposed to be log base 5 of 25 equals 2. There's supposed to be equal signs on these. Equals 2. This one is supposed to be equals -1. I don't know how I missed such a crucial part of the problem. Log base 2 square root of 2 equals 1/2. Sorry, guys. And then the last one has equals. Anyway, log base 2 of 25 equals 2 means, again, we can do our little circle thing. So we start here, go there, so we know 2. And that's supposed to be log base 5. So sorry. Anyway, I'm going to fix that really quickly. Anyway, so we start at 5, we go up to 2, 5 squared equals 25. And 5 squared does in fact equal 25. So, cool. All right, next up we have log base 6 of 1/6 equals -1. Again, 6 to the -1 equals 1/6, which is in fact true. Log base 2 of square root of 2 equals 1/2. 2 to the 1/2 equals square root of 2. Again, which we know to be true. Log base 7 of x equals 5. 7 to the 5th is equal to x. And then we could figure out what 7 to the 5th was if we wanted to actually further solve for x. But again, right now we're just practicing going between logarithmic and exponential notation. So hopefully that wasn't too bad. Because now for our examples, we are going to write as a logarithmic equation. So now we're starting with that kind of like x equals b to the y knowledge, and we are rewriting as logs. So 9 cubed equals 729 means that log base 9 of 729 is equal to 3. Because then again, we would have 9 cubed is equal to 729, which is what we started with. Number 2, 6 to the negative 2 equals 136 means that log base 6 of 136 is equal to negative 2. Okay, and then so that would be 6 to the negative 2, which is in fact 136. Then last but not least, we have 5 to the 1/3 equals the cube root of 5. That means that the log base 5 of the cube root of 5 is equal to 1/3, which will be 5 to the 1/3 equals the cube root of 5, which again, we know to be true. So hopefully you can see it's pretty easy to kind of switch between logarithmic and exponential notation. All right, now our example 3, we are finding the value of each logarithmic expression, okay? So log 4 of 16 is equal to, base 4 of 16 is equal to x, right? Because we want to find that value x. So then we're going to write 4 to the x is equal to 16. Well, 4 squared is equal to 16, so therefore x equals 2, right? And so therefore log 4 of 16 is equal to 2. And we found the value of the logarithm. Okay, let's do log base 10 of 1/10 equals x, which is the value we're trying to find. 10 to the x is equal to 1/10. Well, we know that 10 to the negative 1 is equal to 10, so therefore x equals negative 1. All right, log base 9 of 3 is equal to x, so 9 to the x is equal to 3. Let's see here, and that is going to be the square root of 9 equals 3, so 9 to the 1/2 is equal to 3, so x is equal to 1/2. So these problems are a little bit weirder. These are kind of like the problems we were doing where we had b to the x equals b to the y, and we had to put a common base on both of them so that x would equal y. This is kind of like the same thing. We're looking for those relationships. So these ones are a little bit harder to do, but again, I just want you to start to get comfortable with thinking about logs and exponents, how they're related and how we use them. So part 2 is solving logarithmic equations. So logarithms are useful for very useful for solving certain types of exponential problems. All right, so for example, solve each equation for x. First up, we have log base 5 of x is equal to 3. So we have log 5 of x equals 3. So again, that's going to be 5 cubed equals x. And then we know that 5 cubed is 125, so 125 equals x. Next up, we have log x of 25 equals 2. So this is going to be x squared equals 25, square root each side, so x is equal to 5. Last up, we have log base 3 of 1 equals x. So that's going to be 3 to the x equals 1. And then we know that we could rewrite this with the same base as 3 to the x is equal to 3 to the 0. Anything to the 0 power is 1. And then we know that x equals 0 because, again, we have that uniqueness property that we learned last class. So obviously, when the x is in different places, it's easier or harder to solve for a variable, right? Because if we think about it as like log a of b equals c, you know, sometimes x is a, sometimes it's b, and sometimes it's c. And depending on where x is that you're solving for, it can be easier or harder to find it. So then we have some properties of logs. So log b of 1 is equal to 0, log b of b to the x is equal to x, and b to the log b of x is equal to x. So just some general properties. And then part 3 is about graphing logarithmic functions. So if x is a positive real number, b is a constant positive real number, and b is not 1, then a logarithmic function is a function that can be defined by f of x equals log b to the x, log b of x. The domain of f is the set of positive real numbers, and the range is the set of real numbers. So the domain, which talks about the x values, right, is only positive. So we don't ever use this bottom part of the x's because our x is strictly positive, but our range, however, which talks about y, I lied. We don't use this part of the axis because x is strictly positive and y is positive and negative. Okay, so know about the domain and range of logarithmic functions because that will be a chapter 10 test question. So if you're watching this lecture, make a note. All right, graph the logarithmic function y equals log 2 of x, okay? So first let's write this equation with exponential notation. So if we know that y equals log 2 of x, then we can write this as 2 to the y is equal to x. And then we can, again, just like we normally do, kind of pick x and y values to go ahead and plot. Okay, so since I have this in kind of a weird notation, I have x is equal to 2 to the y, I'm going to go ahead and pick some y values and then solve for my x values, right? Because I know that x is equal to 2 to the y. So x, y values, I'm going to do 0, 1, 2, and -1, okay? And then x equals 2 to the y. So 2 to the 0 is equal to 1, 2 to the 1 is equal to 2, 2 squared equals 4, and 2 to the -1 equals 1/2. Okay, so I have the points 1, 0, 1, I should just delete this. That's not actually helpful. I'm going to draw my own. I thought it was being helpful, but I wasn't. Okay, so I'm going to draw my own. Didn't want to do that. I only wanted to delete this one little point. Okay, so I know that I have a point at 1, 0. I have a point at 2, 1. I have a point at 4, 1, 2, 3, 4, 2. And I have a point at 1/2. It's gonna be right there, -1. Okay. So, oh, I don't know why I put that on the axis. It's the x values 1/2. So then I can kind of see that my graph kind of does this sort of thing, draw arrows on both sides. And here is the graph of the function y equals log base 2 of x. Okay. Let's do one more here. Graph the logarithmic function f of x equals log base 1/3 of x. So again, we're going to write y equals log of 1/3 of x. So then we can write this in exponential form as 1/3 to the y equals x. So as you can see, this is like the inverse of the exponential equations that we were just graphing, which were, for example, y equals 1/3 to the x. But now we have x equal 1/3 to the y. So very clear inverses, right? Our x's and y's are just swapped. Anyhow, let's pick some y values. So we have x, y. Let's pick 0, 1, -1, -2. And again, x is equal to 1/3 to the y. So 1/3 to the 0 is equal to 1. Anything to the 0 power is 1. 1/3 to the 1 is equal to 1/3. 1/3 to the -1. 1/3 to the -1 equals 1/1/3, which is 1 divided by 1/3, which is equal to 1 times 3. That's 3. And then same thing with 1/3 to the -2. We're going to have 1/3 to the -2 equals 1/1/3 squared. 1/3 squared is 1/9, so 1 divided by 1/9 equals 1 times 9/1 equals 9. So now I have some points, and I can go ahead and draw them on my coordinate plane to graph them, right? So I have a point at x equals 1, y equals 0. So x equals 1, y equals 0. That's going to be right here. I have a point at 1/3, 1. So 1/3 on the x and then 1 on the y. And then I have a point at 3, -1. Sorry, that got a little confusing. 1, 2, 3, 3, -1. And a point at 9. Let's say 9 is way out here on the axis. -2. So it's going to be 9, -2. And so that means that I see that my graph is going to come up kind of like this and then go head out that way. And remember, it's never going to come over here because our x values are not negative ever. So we're always going to kind of have some sort of like shape that looks kind of like almost like a, I don't know, like these kind of shapes. Curves, I guess. I don't know how to describe them, like half of a really wide parabola. I don't know. But either way, this is clearly the inverse of exponential functions that we were graphing. So if you were not having any trouble graphing exponential functions, you shouldn't have too many troubles with log functions. And so that's all I got for today. Make sure you practice using logarithmic notation just because it's kind of foreign and new. And we will continue to learn about logs and how cool they are. So that's all I have today. Have a lovely day, guys. Thanks for watching.